So, so today I'm going to talk about holography for AdS subregions. So this is an ongoing work with Tunir, Victor, and Shubhrat. So I will briefly motivate the problem and like why this is interesting to ask such questions. And so we already know the holography in AdS-CFT. This is this has been explored a lot. Like a gravitational theory in AdS is dual to a boundary CFT. So we can visualize AdS like a cylinder, and like CFT is living on this boundary. So if we have some, say, scalar field phi in the bulk, we can say for the time being it is just a normalized modes like near the boundary. So we can extract out these boundary fields, and this boundary fields is actually dual to some CFT operator of conformal dimension delta. And with this, you can just reconstruct your AdS bulk. But the point is, like these AdS-CFT dualities, so these are like based on some dualities of string theory, as Chandra already mentioned. So I will motivate like how we can get like holography from canonical gravity. So if we have this condition satisfied, like this Hamiltonian is bounded from below, and our vacua can be identified with boundary charges, then we can already have some notion of holography within low energy theory. And we call it like a principle of holography of information. So this work has been done by Shubhrat and his collaborators. So what it says, like in a theory of quantum gravity, a copy of all information available on a Cauchy slice is also available near the boundary of the Cauchy slice. So we already visualized AdS like a cylinder. So this time direction goes from down to up. So Cauchy slices are like constant time like slices. So what this principle says, like if we have some excitation in the bulk, that's already been available in this boundary of this disk. So now this principle has been more sharpened by this recent work by Chandramouli, Victor, Olga, and Shubhrat. And this is a perturbative approach, and they were using this Hamiltonian and momentum constants to annihilate the quantum wave functional. So this already Chandramouli has explained just before me. So we can actually identify like this like the states with boundary observables, like this O1, OK. There are some boundary observables, and like if we find like these correlation functions are same, like then psi1 and psi2 are same. Now this is a nice setup, and we can actually apply it to other scenarios. And one of the scenarios is this subregion duality, or like that I am going to talk about now. Now subregion holography. Given a subregion in AdS boundary, so now it is just a constant time slice. It's just a disk. You can visualize like that. Now we are taking one subregion of it, like some say R, and its complement is R bar. So the question is like, what is the bulk dual to this thing? And there are some conjectures by Maldacena and other people. Like this subregion R is dual to some entanglement wedge in the bulk. So the question is, what is entanglement wedge? This entanglement wedge comes to the literature with when people are studying this entanglement entropy of region R. So this region R, so this is some CFT. It is some like quantum field theory system. We can define some entanglement entropy of this, how this region R is entangled with this its complement R bar in some given state. And this is actually like Ryu and Takanagi, and then Rangamani and Takanagi and other people, like they had this formula, like you can find this entanglement entropy of this region R. It can be found with this formula. Here A is the area of some surface which is anchored from this boundary of the R, and so this is the area of this surface, and S bulk is some like say some like a free field entanglement entropy of some in this region, in this dashed region, and we have to make choice of our surface such that this whole thing is like a minimum, this whole expression. Now and if you take this causal diamond of this which containing this region, that corresponds to some entanglement wedge of this region R. So this is only the time slice, and if you take this, it's like a causal diamond, the smallest causal diamond of the containing this region, that corresponds to the entanglement wedge of R. So now, first let's talk about causal wedge. So this is one of the like simplest, or this is the simplest entanglement wedge, and so I think you can I think so I have taken the region R, like the half of this this circle, like it is this blue region is my region R, and this red this thick line is this surface, this minimal surface. And now this now here this wedge is actually this green this vertical green line. So these are like some like boundary some causal diamond of this R. And if you take some intersection of this causal past and causal future inside the bulk, you get this causal wedge. So this is some like simple thing to first study. And see, the one thing is like if you take this boundary causal diamond and this causal wedge, they are just trivially dual to each other. Okay, because this causal diamond is the boundary, and it's the causal extension inside the bulk is the causal wedge. So they are just trivially dual to each other. But subregion duality says something more stronger. Subregion duality says like this: there is duality between R and the wedge. So this is this region R and this and the whole this causal wedge. So and this can be motivated by the fact, like if we have some like local Hamiltonian in the boundary, so then we can actually squeeze all the information of this boundary diamond into this in this single slice, this R. So so now we can also move to some general wedge, which is entanglement wedge. So now this we can take some R as some like union of two like disconnected regions in the boundary. So this is just these red lines. So these are these minimal surfaces here, and this is this the special part of our causal wedges. Now, if you just try to increase its length, like you just make this R region bigger, then at some point you find that these red lines, they are not minimal anymore. So you find this you find these blue lines, these are now like our minimal surfaces. So then this now this we go back to this definition of the entanglement wedge. It is the region between the boundary and the RT surface. So here this boundary is this R and this RT surface is this blue. So it should be the whole entanglement wedge. Now you see like this middle region is not causally connected to the boundary at all. So there is something happening here, like it is some phase transition kind of thing from this causal wedge to the more general entanglement wedge. Okay, so now now I will just mention some puzzles which is already studied, but in some other contexts. So one of the puzzles is some like this unusual localization of information in the boundary. So let's think like this conjecture subregion duality true, let's say. So then say we are taking some point P in the center of the, so these are all some constant T slices. So these are these disks, and this boundary is this circle, and we are just dividing the whole boundary into three slices, three equal parts like R1, R2, and R3. And see this R1 and R3, like they have information about the P, because when you are taking R1 and R3, the minimal surface will be this line, and so it already contains P. But R1 itself does not have any information of P, and it goes like in a circular way, like all like you can find like any two of them together has the information about P, but individually they do not have the information. Okay, so this is some like unusually, like somehow this, like if the subregion duality is true, then somehow like this problem is coming, and like we don't have any sharp answer to it now. Now another thing is that say this like if the subregion duality is true, then this then we can find some modular Hamiltonian. And so okay, I didn't say much about modular Hamiltonian. It is something like Hamiltonian, but it is defined on this region R, and this is actually related to this density, reduced density matrix of this in this region. But if the subregion, sure.
10 minutes.
Okay, thanks. Yeah. Now you can find like this K should have some commutator with this some phi p, and it should give you the flow under this modular Hamiltonian, which is called in literature like modular flow, and we should give you something non-zero. But the point is, if we also if we trace this point P with some other point in this boundary, say on this. So this was my subregion, and this was this causal wedge, and P was inside. And now I am tracing P with some point in the R bar. Now the point is like when I am tracing this thing, so this all the information of P, this degrees of freedom of P are now at this R bar, and R bar are like space-like, so they should commute. So the K with phi, it's giving me 0. So two different approaches giving us different results. So this is a sharp tension with the Wilson line dressings and subregion duality. So we still don't have any sharp answer to about this. And so and one thing is that I already said earlier, like we'll apply this we'll do it formalism to the subregions, and so why it is interesting. So because the current understanding of this RT formulas and the subregion duality is based on Euclidean path integral, and this Euclidean path integral is like a box, like a black box. It gives us results, but we have not much physical interpretation of it. So it would be like very nice if we have some Hamiltonian understanding, like some Wheeler-DeWitt formalism understanding of this entanglement wedge holography, this phase transition, and this and obviously the dressing here. So here I am. Yeah. Thank you. Yeah.
Can I ask a question?
Yeah. Sure.
Yeah. So I mean, the quantum error correction code, in a sense, is a Lorentzian picture, right? I mean, that tries to explain how this subregion duality works in the Lorentzian version.
Yes, but the point is like it is a very toy model. Like it does not like, and also it does not like include the gravitational constant, I think. Yeah, like it is.
Yeah, but I mean, so I'm asking that: are you? Will one of your attempts be to try to get this quantum error correction code picture from Wheeler-DeWitt equation?
Yeah, that is one of our motivation. Like we may get some quantum error correction story from this Wheeler-DeWitt approach, but we are still working on it. Yeah.
Okay. Oh, thank you.
Does it answer your question? Yeah.
Thank you.
Hello.
Yeah, sure.
So what do you mean by gravitational dressing? You have mentioned.
Oh, acha. So this, so like in gravity, so there is no local gauge invariant operators. So you have to like when there is a boundary in your manifold, so you can dress. So you in your all your this local gauge degrees of freedom, they die out in the boundary. So you can have some notion of locality in this boundary. So you just dress with some Wilson line from the boundary here.
Okay.
At this point, you attach a Wilson line from some boundary point here, and it gives you some gauge invariant operator. Yeah. Okay. In that sense. Yeah.
Thank you.
Yeah.
Can I ask something?
Yeah. Sure.
Yeah. What would this explicit dressing look like? P to R bar. Like what would it look like explicitly?
There are some paper by this Giddings and I think they have some way of dressing, but we will calculate these dressings from our Wheeler-DeWitt approach, like, because see this in the first this when we are saying like these wave functions are like invariant, so these wave functions are actually gauge invariant. So we can also have some notion of gauge invariant operators from this Wheeler-DeWitt approach. So we have in our we have something in our notes, but we have to make it more precise. Like so there is already some work done by Giddings for with this Wilson line approaches. Like they have some precise result, but we have some another approach to do that.
I see. Okay.
Thanks, Priyadarshi.
Thank you.